Hi, my name is Grace Ahmed. I'm a master's student in complex systems and a mother of five, among other things. For the past several years, I have been connected to a local parent-child center as a participant and as a community organizer and volunteer. In my current role on the Monitoring and Evaluation Committee, I've often wondered if network science can provide any tools to help quantify the community building at the family room. How can we put a number on the bringing together of families from all walks of life, widely varying income levels, and a rich diversity of ethnic and cultural backgrounds? How can we measure the strength of community connection? Can we show some centrality of this subcommunity between normally disparate groups that mix infrequently elsewhere? So this, as motivation, plunged me down the rabbit hole of asking, what do real social networks look like? How do we know? And how are social networks modeled?
How are these networks different than all the other networks?
Social networks have distinct qualities compared to other types of networks like gene networks or communication networks. Specifically, they are marked by high clustering and homophily.
How do we know that?
There are surprisingly few real-world social networks that have been studied to establish typical characteristics. Bipartite graphs of film collaborations and scientific collaborations have been commonly used because they are easily accessible, but there is some question whether these are true social networks at all or whether they are more accurately described as economic networks. Common social network data include the karate friends we've used in class. This set, along with film collaboration, was used in a 1998 paper by Watts and Strogatz, the only data used to generalize that social networks have high clustering and homophily, and this influential work is frequently cited in describing properties social networks are assumed to have. Other network canon includes the Southern Davis Women data, information about 18 white women socialites attending events over 9 months in the 1930s. One wonders if this bias sample can be a great representation of all the social networks. Online social networks are also frequently studied, especially Twitter data, by virtue of accessibility. Analysis of follower and followees on Twitter shows non-power law follower distribution, a short effective diameter, and low reciprocity, a deviation from known characteristics of human social networks. However, looking at direct interactions on Twitter shows a sparse and hidden network of connections underlying the declared set of friends and followers. Snowball sampling has been used to measure social attributes and probability of social connection in specific networks. In people who inject drugs in rural Puerto Rico, HIV status and having been in substance abuse treatment were predictive of edges in the network, while other attributes like age were not. Some other methods have been used to study real-world social networks. One too fun not to mention is a Korean study of social tie formation, where participants were invited to a series of offline social events where they wore radio signal strength indicator devices, so researchers could tell who they interacted with at the event and compare this to the growth of participants' Facebook social networks. How are social networks modeled? Much of the sociological research continues to use statistical models. While network science has brought us small world networks, caveman networks, scale-free networks, geometric preferential attachment, network growth by closing of triangles, analysis integrating spatial and social analysis, models based on social distance attachment, and more recently, analysis of changes in networks over time, and opinion spreading on social networks. Part of my project was creating a widget for network visualization at seethenetwork.com using Python, Flask, and cytoscape.js. At the website, the user can choose a type of network construction, specify some tunable parameters, and choose from a few layout options for the network visualization. We can start by looking at the familiar small world model, specifying the number of nodes, the number of initial links, and the probability of rewiring. Make the network, and then we can view on a circle layout to easily see the structure. There is an option for a pure scale-free network, but we'll look at a more interesting example, which uses a modification of the Barabasi-Albert algorithm, which allows preferential attachment based on homophily of a node attribute in addition to node degree. Here, the node attribute is a binary quality, and we can tune the proportion in each of the two groups. As the homophily is increased, we see more segregation of the two groups in the network. Next, we'll create a network using Euclidean social distance, described by Baguna. There are a few choices of distributions to create the social attributes, and we'll look at a bimodal distribution built from two normal distributions with equal variance. This last parameter is a measure of homophily. At the lowest level, the network is a nice ball of spaghetti. As we tune it up, the two groups will separate from each other more. There are a lot of ways this site could be improved, like including instructions for how to use and tune the different models. I hope you'll take a few minutes to play with the widget and see what you find.